Everyone. My topic is random variables and random process. So before a quick introduction, we need to know what is the random variables and random process. Let's take a real life example. We see random process everywhere around us. Like the modern example for a random process will be the self-driving cars. Let's consider one Tesla car. We know that modern self-driving cars can do many things without a driver, that's a human driver. So a artificial intelligence built into it with the help of the probability that occur by its knowledge, that is can decide whether to go straight, turn, stop, or apply brake. Everything has trained it. So it's a perfect example of the probability that we apply on our day-to-day life. So let's take the what is the topic I'm discussing here is random variable concept, cumulative distribution function and its properties, probability density function and its properties, mean square value, variance, moments, special random variable that are Gaussian random variable, uniform distributed, Poisson, exponential random variable, and Rayleigh. And then the central limit theorem, joint distribution function, properties like correlation and orthogonality, covariance, correlation coefficients. So let's take a walk among the random variable area. The random variable concept. And at the first, random variable is a rule of function by which we assign sample points to a real number. That means a physical sample space is a collection of set of values that will be occurred by a process or a experiment will be conducted by us that is mapped onto the real number line, that is from minus infinity to infinity. Now from the figure we can clearly see that the lambda 1, lambda 2 and lambda 3 belong to the sample space S. Here we can see the sample space S. The lambda 1, lambda 2 and lambda 3 are the sample points belongs to the sample spaces, and we are mapped the sample points to the real number line. And since we want to analyze we need to do a specific task on this. So that now we have a random variable, we can perform some operations on it according to our needs, like the CDF, PDF, PMF, which are the cumulative distribution functions, probability distribution function, probability mass functions, like that. And we have classification on random variables, which are the random variables are classified according to the sampling instance, or like continuous random variable, discrete random variable, and mixed random variable. By the way, mix will be include both of the continuous and discrete variable. And by specifying a random variable, I mean that specifying a random variable means being able to determine the probability that x belongs to a set A for a Borel set A that is belongs to R. In particular for an interval A to B, which B include. And we have to say about cumulative distribution function, CDF. We need to be able to determine that probability of x belongs to A for a Borel set A belongs to R, that is any set generated by starting from interval and taking countable unions, intersections and complements. from the figure, we have see a graphical representation of the CDF. By the way, in real life CDF, just the function means just adding up the already occurred values to a particular value, the probabilities, and the probability mass function PM of which will be a random variable is said to be discrete if f of x consists only of step or the control set x, and a discrete random variable can be completely separated specified by the probability mass function, that is Pm of Px of x equal to Px equal to x for every x belongs to x. And clearly that's a Px x of x greater than equal to 0, and P belongs to and Px belongs to x, Px of x equal to 1. Then the probability density function PDF. A random variable is said to be continuous if its CDF is a continuous function, and we have, let's say, with the CDF it's if it is continuous or not, and this PDF CDF x obtained by fx of x equal to integral minus infinity to x fx of u du for continuous. The expected value of a random variable, which we say mean, and the expected value of a random variable is given by, we denoted it like e of x over mu equal to sigma of x of I, p of x equal to x of I. That's for a discrete. For continuous, e of x equal to minus infinity to infinity integration minus infinity to infinity s fx of x dx. And we know the expected value is called mean of the random variable x, and denoted by mu of x, mu suffix x. Then the another factor is the variance sigma of x square, that is equal to e of x minus mu of x the whole square. And in the one word, the expectation or mean is the most probable, or we can expect that value from that entire random process. And variance is it's almost like the deviation from the mean value. And another classification is the different random variables. We have univariate random variables, multivariate random variables, and the univariate random variables. Again, we classifying it as continuous and discrete. Talking about the continuous univariate random variables, first of all, the uniform random variables. We have the uniform, Gaussian, etc. Many of that. Let's analyze the factors and PDF, CDF parameters for each of these. For uniform random variable, we have parameters let a and b, and will the mean of the random variable will be half a plus b. Variance will be b minus a whole square by 2, and the PDF 1 by b minus a for all x belongs to the interval a to b, a comma b, 0 otherwise. And then the CDF will be 0 for x plus than a, x minus a by b minus a for x belongs to a interval a comma b, 1 for x greater than or b. And the Gaussian random variable, we will be talking, it's also called the normal random variable. We will be talking about the Gaussian processor details in a moment. And in probability theory, a normal or the Gaussian Laplace Gauss distribution is a type of continuous probability distribution for a real valued random variable. The generation from this of its probability density function is the f of x equal to 1 by sigma root of 2 pi into the e raised to minus 1 by 2 and x minus mu by sigma the whole square. That will be the function f of x at the mean mu variance sigma square. We will be talking about this in details later. Let's analyze the next. The next thing will be about the exponential random variable. In probability theory and statistics, the exponential distribution is the probability distribution of the time between the events in the Poisson point process. That is a process in which events occur continuously and infinitely at a constant average rate. It is the case of a gamma distribution. It is the continuous analog of the geometric distribution also, and it has a key property of being memberless. And the mean for the exponential random variable will be 1 by lambda. The variance will be 1 by lambda square, where lambda is the parameter. PDF equal to lambda into e raised to minus lambda into z. CDF will be 1 minus e raised to minus lambda z. And clear that for the exponential random variable. And let's look at the next portion. The next is the discrete type random variables. There will be the uniform random variable first. We have the uniform discrete and uniform continuous random variables. That will be vary according to our sampling needs. The uniform random variable, the discrete version will be in a probability theory and statistics. The discrete uniform distribution is a symmetric probability distribution where a finite number of values are equally likely to be observed. Every one of the n values has equal probability 1 by n. Another way is saying discrete uniform distribution would be a non-finite number of outcomes equally likely to happen, equally likely to occur. The PF for the uniform discrete random variable will be 1 by n. Let's have a look at the binomial random variable now. The binomial random variable in probability theory and statistics, the binomial distribution with parameters n and p is a discrete probability distribution of the number of success in a sequence of n independent experiment, each asking a yes or no question, and each with its own boolean valued outcomes like the success O bar x bar true bar 1 with the probability p, and the failure bar no bar false bar 0 with the probability q will get 1 minus p, and that will be the total probability 1 minus the probability of being true or success, that q equal to 1 minus p. A single success or failure experiment is also called a Bernoulli trial or Bernoulli experiment, and a sequence of outcomes is called a Bernoulli process for a single trial. That means n equal to 1. The binomial distribution is a Bernoulli distribution. The binomial distribution is the basis for the popular binomial test or statistical significance. The mean for the binomial random variable will be n into p. Variance will be npq. The PMF will be the n of k, p of p raised to k, q raised to n minus k, where the n of k will be factorial divided by k factorial into n minus k factorial. The next type will be the Poisson random variable, which is an example for the discrete random variable. The in probability theory and statistics, the Poisson distribution, uh, named after the French mathematician, the Simon Dennis Poisson, is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time in space. If these events occur with a common constant, with a non-constant mean, right, and independently of the time since the last event, the Poisson distribution can be also be used for the number of events in the other specified intervals such as distance, area, the volume, and the Poisson distribution will be very useful for us. The mean for the Poisson distribution will be the lambda, where the lambda is a parameter, and the variance will be the also lambda. The PMF will be lambda raised to k e raised to minus lambda will be k factorial. We'll be seeing a example of the Poisson distribution now with a problem. Now we are talking about the Poisson random variable. Let's take an question example for the Poisson random variable. It's a question: a telephone switchboard receives 20 calls on an average during an 1 hour. Find the probability that for a period of 5 minutes no calls is received. Exactly 3 calls are received, and at least 2 calls are received. And this is a pretty interesting question here. And here we are observing phone calls received for an hour or a unit interval of time. We can assume a Poisson distribution here. So the Poisson distribution for P of x equal to k equal to e raised to minus lambda less to k factorial, where k equal to 0, 1, 2. Now the first, also lambda is a parameter, so we need to set the parameter which will be common for the 3 cases. 20 calls in 60 minutes, that will be lambda equal to 20, but we are observing for a period of 5 minutes, so for 60 minutes lambda equal to 20, then for 1 minute lambda equal to 1 by 3, for 5 minutes lambda equal to 1.65. So we set the lambda. Now we have to find the option A case. No calls is received, that is k equal to 0. So k will be the varying factor. So p of x equal to 0. We need to find that. That will be e raised to minus 1.65 bracket into the 1.65 raised to 0 factorial. That will be eventually e raised to minus 1.65. And the next case is exactly 3 calls are received. So the k will be 3. PFA, the probability of x equal to 3 equal to the usual equation e raised to minus 1.65 into 1.65 e raised to minus 1.65 into 1.65 raised to 3 by 3 factorial. And for the next case, it's a little tricky. At least 2 calls received, that means that at least 2 calls, so more than 2 calls are possible, but 2 calls will be necessary. That means probability of the x greater than or equal to k, where k can be 2, 3, etc. And that will be the 1 minus probability of p being probability of being x less than k, and x less than k will be definitely 2 values. 1 minus the probability of x equal to 0 plus the probability of x equal to 1, that will be eventually getting 1 minus e raised to minus 1.65 into 2.67, solving, we get the answer. So we discussed about the random variables, and let's take a look at the random process area. And basically the random process, the random variable will be given from the random process. So let's talk about the random process. The sample space is a product we get from the random process, the random experiment. And the sampling of the random process will give random variables, which means from the graph in the figure graph we can see that the sample space here is the S, like we saw previously. Lambda 1, lambda 2 are the sample elements. We plot the function for the sample elements like the as shown in the figure. These are the plot of, and if we the sampling instant will give us the random variables like we sample at t1 and we sample at t2, and that is tfi tfj in the figure. That means eventually if we draw a vertical line in the graph, we get the random variables on this graph. That's all of that. Just talking about the random process again. When a random variable outcome becomes a function of time, it can be called as a random process. Random process may be a task of a thought of a process where the outcome is a probabilistic, also called stochastic, rather than deterministic in nature. That is where there is a uncertainty as to the result. So these are some examples of the random process, which are the common examples. Tossing a die, we don't know in advance what number we get. We have 6 faces for a die. That is eventually everyone knows that. And flipping a coin, which will be the universal example for the random process. Like if we hatch carefully enough device and apparatus to flip a coin, it will always come up the same way. However, normally flipped by a human being can be considered random process. So a human being tossing a coin will be unbiased, by the way. So it can be considered as the random process. And the shaking up of a clash of balls in the hat and pulling out one without looking, that also will be random. Let's talk the two ways to view the random process. Random process can be viewed in the function of x of t comma omega of two variables. The time t belongs to the interval t, and the outcome of the t belongs to interval t, and the outcome of the underlying random experiments omega belongs to capital omega. Fixed t, the x of t comma omega is a random variable over that is that, like we have already said, if we draw a vertical line on the graph, we eventually get the random variable. Let's talk about the next big thing about here is the autocorrelation. And there are some expectations, the operations we need to consider, which are like the autocorrelation, stationarity, wire spectral density, and firstly autocorrelation. Autocorrelation is simply the Pearson correlation between values of the process at different times as a function of the two times of the time lag. That means we are correlating a function by itself, that is autocorrelation, by shifting the function by a lag. And the correlation, autocorrelation equation will be the Rx, so we denote it as Rf xx of t1 comma t2 equal to the expectation e of x of t comma x bar of t2. The stationarity and the stationarity process. While talking about stationarity process, by definition in mathematics and statistics, the stationarity process is a stochastic process whose unconditional joint probability distribution does not change when shifted in time. Consequently, parameters such as mean and variance also do not change over time, which is also called Stigson's stationary process. That's another name for the stationary process. We call generally SSS. We call it SSS. For many applications, strict sense stationarity is too restrictive. Other forms of stationarity such as wide sense stationarity, what is WSS, or the nth order stationarity are employed. The another impressive term with is the power spectral density or PSD. The power spectrum of a time series x of t describes the distribution of a power into frequency components composing that signal. That according to the Fourier analysis, any physical signal can be described into a number of discrete frequencies or a spectrum of frequencies over a continuous range. The statistical average of a certain signal or sort of signal, including the noise, as analyzed in terms of its frequency content, at A is called its spectrum and hence the power spectrum. Now, talking about the power spectral density, we can say that the area under the PST curve gives the average power, and some important properties of the PSTs are the we can denote the PST as Sx of f is always real and non-negative, and the Sx of f equal to Xx of minus f, the average power equal to integration minus infinity infinity Xx of f df. Now let's talk about these are the some random process example about the mainly power spectrum process and white noise random process, which are very important in probability theory and statistics. A Gaussian process is a stochastic process which such that a very finite collection of those random variables has a multivariate normal distribution, that is the a very finite linear combination of them is normally distributed, and the Gaussian random process like n of t with a probability distribution that is flat over a wide range of frequencies is called the white Gaussian noise, which is we are familiar about the SNN of and is denoted by the SNN of f equal to the n0 by 2 in between the minus infinity less than f less than f infinity, and that's a problem for the Gaussian process. Let's talk about the white noise. uh, we are familiar with the white noise. Let's according to the definition, in signal processing, white noise is a random signal having equal intensity in different frequencies given in it a constant power spectral density. The term the term is used with these or similar meanings in many scientific and technical disciplines, including physics, statistical engineering, telecommunication, and statistical forecasting. White noise refers to a statistical model for signals and signal resources rather than to any specific signals. White noise draws its name from the white light. All those light that appear white generally does not have a flat power spectral density over the visual. And uh, talking about generally the white noise is, we are all familiar with this in given the diagram. The white and gray shade which will be all seen in the television screens, old television cable TVs, which is caused by it's not no signal conditions. The signal appearing in the television while having this in the screen will be the white noise. That is uh, the noise is only not the white noise in that much about the pink noise like something, but the white noise is most common. The white noise, that is uh, that's all for the presentation. Thank you. And that's for the presentation. Thank you. Thank you.